Okay, so in this section we'll talk about fundamentals of price theory and specifically how prices emerge in a world of perfect competition. And earlier when we talked about demand and supply, the implicit assumption was always that we have lots and lots of people on the supply side and lots of people on the demand side. So now what we do next is we first want to take a look at a typical firm within the world of perfect competition, and we want to look at their production and cost. And then later we will take a look at how that unfolds in the marketplace. But let's start with production and cost. And let's jump right into it. So here you see basically two graphs, which is a typical short-run cost curve. So the first thing that's important is in economics, what is the short run? In economics, the short run, in production at least, is always the time in which you need to operate with a fixed capital stock. So think about it like I have costs when I cook something in my kitchen, but in my kitchen the capital that I have, which is the stove and the oven and the refrigerator, they are fixed. So I have to work with that fixed capital. But if I ever move into a bigger place and maybe I have a bigger kitchen, then the short run of my old smaller kitchen has ended and I move now to a larger kitchen. So again, the short run refers to fixed capital, which is assumed to be constant in the short run. Okay, so what do we do in production? So here you see a production function, and what we do in production is we convert input into output. So that is simply a production function. So we convert input into output. That is production. But a production function is subject to certain dynamics which have to do with specialization gains, something that already Adam Smith identified, which means that if I have, for example, think of the input as labor. If I stand alone in my kitchen, well, I can produce something. But if somebody helps me, we can engage in specialization gains, and we can specialize. One is doing one thing, the other one is doing something else. And what happens is that initially output grows faster than input. So that is represented by the upward sloping production function. So as long as the production function increases faster than output, it is upward bend, and during that time we have positive and increasing specialization gains or marginal returns to labor. So let's think about it. The way you can think about it is, and maybe later I'll talk more about it, I have labor input. So let's say I'm alone in my kitchen, and so we have labor. And so first, of course, if I have nobody in the kitchen, there won't be no output. So output will be 0. Well, if I'm alone in the kitchen, so I have one labor input, maybe output goes up to 1. So I can produce maybe 1 cake. But if I have two people, so I have somebody helping me, maybe output goes up to 3. And maybe I have another person helping me, we still can specialize, and maybe total output goes up to 6. And maybe if a fourth person comes to my kitchen, maybe total output goes up to 10. But now slowly it gets a little bit crowded in my kitchen, and if a fifth person comes, well, maybe total output still increases, but now at the lower rate. Maybe total output is now only 13. And now maybe I have a 6th person. Well, it's still good to have a 6th person, and maybe total output goes up now to 15. And let's say I have another person helping me, the last one, 7, and that person still adds a little bit of value, but total output now goes only up to 16, because we start standing on each other's feet. So now if we take a look at this output and we compare it, or we look at it and we look at the marginal output, or in this case specifically the incremental output, but I just call it marginal output. But technically it's the incremental output. But the idea is the same. So what that means is incrementally, if I increase input from 0 to 1, the output increases from 0 to 1, which is plus 1. If I increase the labor input from 1 to 2, now output goes up from 1 to 3. So now we have marginally or incrementally a plus 2. The third person adds another 3. The fourth person adds another 4. But now we have reached the maximum of the specialization gains, because as soon as the fifth person enters, the marginal output is still positive, but it starts to decrease again. It's only again plus 3 from 10 to 13. And the sixth person adds another plus 2, and then we are down to plus 1. So that is basically the idea. So if we look at production, as long as maybe you can't find the dark green. So initially, if you take a look, is that this slope increases at the faster and faster rate. It gets steeper and steeper, but then after a certain point, output still increases, but at a smaller and smaller rate. And the marginal is technically the slope of the curve at any point. You can see down here the slope is very flat at each point, but then it gets steeper and steeper and steeper. And then once we reach the maximum marginal output, which is in our example the fourth person, well, the output still goes up, but the slope at every point becomes flatter and flatter. And that is captured here. So the marginal output function of a typical production function first increases. So it first increases and then it reaches a maximum. The maximum is here. But then the marginal output still stays positive, but then goes down again. Okay, so we can also take a look at the average output. So the marginal output is the slope at any point, and mathematically we would say that the marginal output is the first derivative. So the marginal output or the marginal product is the first derivative of the total output. That should be the total output. I call that the output. If I can fit it in here, the output with respect to the change in input. That's the marginal product. And the average product, I just call that actually the average labor product, ALP, because our input factor is labor, is simply total output over total labor. Okay, so if we take a look at the average labor output, so the average labor output is at any given point the total output. So let's consider this point here, exemplary, point A. So what is the average labor product at point A? Well, it is total output, which is this distance, over total input, which is this distance. Okay, so now if we combine if we take a look at that slope of this triangle, we can see that this slope must be the average labor product. Let's take this point here. Let's say point B. Okay, at point B, total output is this distance here, and total input is now much longer. So now if I take a look again at the rise of this triangle, you can see that the slope is becoming steeper. So the average labor product has gone up. But this point here, point B, is close to the maximum of the marginal product, but it's not the maximum average labor product, because the average labor product is maybe here in point C. Why? Well, in point C, this distance here is total output, and now total labor input is this distance. So now take a look at what happens if we take a look at the slope. What do we have here? At this point, the slope intersects with the marginal. It's the same slope in that point. So in other words, whenever the marginal output is in its maximum, which is, I don't know, maybe roughly here, so here is the maximum of the average labor product, it must be equal to the marginal product. So if you take a look at the average labor product, which is this blue line here, so now here's the maximum, and it intersects exactly where the marginal product is. Okay, so in other words, whenever the marginal is equal to the average is in its maximum. So again, here's the maximum. Well, you can see it here too. Okay, so we can also derive that mathematically. So we can also say, prove, so the average labor product is the output, Q, I call it Q now, output is Q, over L. So the average output, let's call output Q, then we get Q over L. And Q is a function of L, and we have to divide by L. So now we need to know certain derivative rules, and I'll just show it to you quickly. There is something which is called the product rule, and it basically says if you have a product like U times V and you want to take the derivative of this one, then the rule says U prime V plus V prime U. Okay, so in order to apply that formula, we can write the average labor product, which is Q over L. Well, we can also write it as Q times L to the negative 1. So now Q, this would be, let's say, U, and L is V. So now we have some space here, maybe here. So then if we take the derivative, so we take the derivative to dq with respect to dl. Okay, so if we do that, we get dq with respect to dl, that is u prime, times v. V is still, so this is also u, and this is v. L raised to the negative 1, that's v. So we get for the first part dq with respect to dl times 1 over L. Okay, that was the first part. Minus, okay, so now minus the 1 from the L, because we do v prime times u, minus 1 times L is negative L raised to the negative 2. So we get for this term 1 minus 1 over L squared, but we still have the Q, which is here, times Q. And in the maximum, that slope needs to be 0, right? So that's the slope here is 0. So therefore we get dq over dl times 1 over L has to be equal to 0. So we can also, of course, then write, okay, so what did I do here? So dq over dl, that's the marginal product of labor, times 1 over L. The second term I put on the other side, which is Q over L squared. Well, now I just multiply both sides by L. So then I have the left side by L, but it cancels out here. 1 over L times L, well, that's L. You see, if I multiply both sides by L, then, well, this L cancels out with this one. And then if I have an L still here, then this L cancels out with one of the L squares, which is LL, and then we get dq over dl, that is the marginal product of labor. So this is basically, you know, a triangle here, where we have here the change in Q and here the change in L, equals Q over L. So that is the proof that in the maximum of the average labor product, it must be equal to the marginal product. So that is just the small proof. So now let's take a look at the cost function. And so what kind of cost do we have? So we have fixed cost, and fixed costs are independent with output. Then we also have variable cost, and variable costs, they do vary with the output. And then in economics, we also like to distinguish between direct or explicit costs or out-of-pocket expenses. And those are things like expenditures for wages, raw materials, rent, interest rates, those kind of things. But for economists, what is very important for economists are the indirect or the implicit or imputed costs, or the economic costs, which is the costs that do not have a cash expense, like could be capital depreciation or the business owner not paying herself a salary. So that would be an opportunity cost. So if, let's say, I run a shop and I could alternatively make a certain amount per month by being employed somewhere else, well, I forego that. That's a cost, that's an opportunity cost. And that's also part of all our costs. So, okay. So, but the point is here, we can see the fixed cost. So here what we do is, we have now output translated in total cost. So, just to see again what we did. So first, we took input, like labor, and converted it into output, call that Q. And then we got a typical production function, which looks like this. So a typical S-shaped production function. And then we took a look also at the marginal product of labor, and the average product of labor. And we said the marginal product of labor has here its optimum, maybe that corresponds to this value here. So let's say if this is 3, then this would be 3. And we said the marginal, the average product of labor has its maximum maybe here. Maybe assume that value is 4. So then here at 4, the marginal product has its maximum, so that would be here. So that would be the average product. So that's what we did. But the point here is we converted labor input into output. When it comes to the cost function, what we now do next is we convert So now what we do is we convert our output Q into total cost, TC. And you see here we have the fixed cost. So because no matter what we produce, the curve starts at 2, so that means we have fixed cost of 2. This is the fixed cost, and everything on top of it is the total variable cost. And you see this cost curve looks like an inverse U-shaped. So here we have the fixed cost, and then we have here on top, suddenly that looks inversely U-shaped. Okay, so now we can also derive again from here 3 important curves, namely the marginal cost and the average total cost and the average variable cost. So down here, the red function, so this one here, that is the marginal cost. So that's the marginal cost. And what is the marginal cost? Again, the marginal cost is essentially the slope of the total cost function at any point. So this is our total cost function. And so now here, if you see, if you put at any point the slope, here the slope it's really steep, very steep but less steep, and it gets less and less steep. Maybe here's the minimum. So the minimum of the marginal cost, which is the cost, the extra cost that you face when you increase the output by a little bit, has its minimum here. But then, the slope picks up again and gets steeper and steeper. So that's why the marginal cost function looks U-shaped. Okay. So here we have now output Q, and the marginal cost function looks like a U-shaped. So that's the marginal cost. Okay, so now let's take a look at the average variable cost. And the average variable cost, let's make that green. Maybe in a green we can see it. So the average variable cost is here. And you see they have a minimum where they intersect the marginal cost function. So why? So what are average variable cost? Well, average variable cost is total cost. Total variable cost. Total variable cost over total output. So again, let's assume we have point A. Let's say point A is here. This is point A. So then the total variable cost is this distance, and the total output at this point is this distance. So now we get again a slope, and you see the slope is pretty steep. Well, let's take next this point, point B, the minimum of where the inflection point is. So here, this vertical distance is again total variable cost, but now we need to divide by this distance of total output, and you can see that the slope becomes flatter. But the question now is, where do we have the minimum? So let me see if I can maybe just draw a straight line. Okay, let's see if that works. So now I take this one. Didn't work, but I can do it differently. Let's say I'll insert here a straight line, and maybe let's make it green, and maybe a little bit. So now if you see, what I do is I'll try to find the point where there is the minimum slope and I'm still touching the total cost curve. So you see I move along the curve, the slope becomes initially flatter and flatter. So the minimum is maybe somewhere here. Maybe the minimum is somewhere here. And then if I draw it correctly, that should correspond to this point. So the same thing for the average total cost. For the average total cost, I just need to find, so now we have to make it maybe blue. So now at this point here, it's point A, total cost, so total cost, average total cost is total cost over Q. Okay, so in point A, we will get the slope where this is the total cost over total output. Okay, but then if I just move along again the total cost function, you see the slope gets flatter and flatter and flatter, and maybe here slightly to the right there is the minimum of average total cost. So maybe, okay, so you get the idea. So both curves are inversely related, inversely shaped, and the average total cost has its minimum where it intersects the marginal cost, so here, and the average variable cost is below, but also has its minimum where it intersects the marginal cost. So here we have the marginal cost. The green was average variable cost, and the blue was average total cost. Okay, so this is the typical cost function, but why is it the cost function inversely S-shaped? Well, if you assume that every worker gets the same wage, so let's say everyone who helps me, I pay them the same wage. So that means I pay everyone the same, but then each worker has initially more and more output. That means that my output grows faster than my cost. Only when the workers start exhausting their specialization gains, then the extra cost grows faster than my total output, because the workers become less productive. Okay, so let's maybe quickly stop here, and then in the next video I will just review everything again from scratch using a different format, and maybe also going back to this example here. But so for the videos not to become too long, let's just stop here and continue with a new video where we then also derive the proof that the minimum of average variable cost intersects the marginal cost. But let's stop here quickly, and then see you in the next video.